Good morning. I am Rik Gupta, final year undergrad scholar at Manipal Institute of Technology, Manipal. Today, I would be presenting my paper on TL-shaped circular parasitic compact radar antenna for 5G microwave applications under the supervision of Dr. Manish Varun Yadav and Dr. Sati Varun Yadav. CST Microwave Studio was used in designing and simulating the proposed antenna design. 5G is a fifth generation mobile network. It is a new global wireless standard after 1G, 2G, 3G and 4G networks. 5G enables a new kind of network that is designed to connect virtually everyone and everything together, including machines, objects and devices. Higher performance and improved efficiency empower new user experiences and connects new industries. 5G or fifth generation wireless technology operates across a range of frequency bands. These frequency bands are categorized into three main groups: low band, mid band, and high band, also known as millimeter wave or mmWave. Each of these bands has its own characteristics and uses. First, low band. This includes frequency below 1 GHz. These frequencies offer good coverage and penetration through obstacles but generally have lower data rates compared to higher frequency bands. They are suitable for providing wider area range and are often used for rural and suburban deployments. Second, mid-band. This range includes frequencies between 1 GHz and 6 GHz. Mid-band frequencies offer a balance between coverage and capacity, providing moderate data rates and reasonable coverage area. Many initial 5G deployments use mid-band frequencies. Third, high band. This band includes frequencies above 24 GHz, often referred to as mmWave. High band frequencies offer extremely high data rates but have limited coverage and are sensitive to obstructions like buildings and trees. They are suitable for dense urban areas and places with high data demand. Outline of the PPT is: first we will start with the introduction, then design of the antenna, then we will go to the comparisons of published antenna, and lastly conclusion and references. Antenna plays a crucial role in aerospace communication by transmitting and receiving radio signals between aircraft, satellites and radio stations. A wide range of antennas including semicircular, L-shaped, triangular, multi-slot and U-shaped antennas are used in aerospace communications. Techniques like changing the ground plane with parasitic elements, adding a small fractional component, U-shaped or circular slots and circles are discussed to enhance their performance. Polar radiation patterns can be created by altering the circular patch or by cutting a rectangular piece. In this paper, we have designed a TL-shaped circular parasitic compact radar antenna for 5G microwave applications. Substrate used in the antenna design is FR4 inscribed on copper anode with overall dimensions as 13 mm cross 15 mm cross 1.5 mm. The RA and RB represents the length and width of the antenna with dimensions 13 mm and 15 mm respectively. RC represents the thickness of the substrate, which is 1.5 mm. The antenna's front side consists of L-shaped, T-shaped and inverse T-shaped elements respectively. Back side of antenna consists of three parasitic rings on top, four horizontal strips arranged in increasing order, and ground plane with small rectangular slots in it. Moving on to results, first we have return loss graph as shown in figure 2, whose frequency ranges from 3.2 to 6 GHz band. Then we have gain and efficiency curve, whose high gain is 4.81 dBi and efficiency is 82%. Then we have IP impedance curve. Figure 4 displays an IP impedance curve that reflects the frequency curve for the proposed design simulated real and imaginary components. The behavior is inductive within the 3.2 to 4 GHz frequency range, followed by a capacitive behavior. The inductive behavior is represented by a positive polarity, whereas a negative polarity indicates capacitive behavior. The curve illustrates the impedance normalized to 50 ohm. Going on to radiation pattern. The radiation pattern of the antenna is in two planes, that is E and H plane. The H plane is defined by phi equals to 0 degree at X or Z plane, and E plane is defined by phi equals to 90 degree at Y or Z plane, which satisfies the required monopole characteristics. Hence, we can say that our antenna is monopole antenna. Going on to surface current distribution. Figure 6 displays the surface current distribution from front to rear perspective. The equivalent surface of the antenna represents its radiated current field and highlights its signal strength, with the ability to generate both E field and H field, indicating significant signal strength in the design. Last but not least, radiation lobe. Figure 7 shows a simulated radiation lobe pattern of the 5G antenna. The front plane of the structure and the frequency distribution of the 2D vector surface current at 3 GHz. The radiated field will closely mirror the surface current of the original antenna by substituting similar surface currents for the antenna. This indicates that even in the absence of main current source, the current can help detect radiation. Going on to comparison of published planar antenna. Now we will be comparing the published planar antenna with the presented planar antenna. Comparison table shows that the presented antenna is more efficient in terms of efficiency and size. From the presented design, we can conclude that size of the proposed antenna is very small, that is 13 cross 15 cross 1.5 mm3. The proposed radiator has a high gain of 4.81 dBi and an efficiency of 82%. The presented antenna is appropriate for 5G microwave communication applications from 3.2 to 6 GHz. The impedance bandwidth of the design is 60.8%. The proposed design has a completely stable radiation pattern. These are the references from which we took help from. That's it. Thank you so much.